Hey everybody. In this video we're going to use technology to help calculate absolute areas. So let's recall what the strategy is for finding absolute area. You essentially identify your integration variable. In this case it's the variable that corresponds to the horizontal axis, and you integrate from the smallest to the largest value, which encompasses your region, and you have to integrate the top function minus the bottom function. And of course we can do this with respect to the vertical variable as well. You just have to sort of turn your head and interpret appropriately what the top and the bottom would be and what the smallest and largest value of the integration variable would be. But the template is still the same. Top minus bottom gives you the height function, which you integrate from the smallest value of your integration variable to your largest. We'll start with an example using the TI-84. So here's a region which is defined by two different curves. We'd like to find the area here of this ribbony shaped region. Now, caution, we seek absolute or unsigned area. We really don't care where the relative position of the axes are. We just think of this as an object we want to paint, say. We really do want to know what the physical area is of this shape. So, we're going to use the calculator approximation. A lot of work on the calculator, and we're going to store, first of all, our functions into what we can call function registers in the y equals screen. And so here is where we store 2 sine x, and then in the register y2 we'll store the exponential function 1/2 e to the x minus 1. A quick plot here indicates that we're in business and we've got the region we care about. Now we need to figure out how to go about finding the area. Certainly we'll be interested in these two intersection points since they clearly constitute the smallest and largest value of x on our region. But we'll notice something else. When we look from the bottom to the top, the description of the top and bottom changes. I mean, in particular, first, we start with y2 being the top function and y1 being the bottom function. But then there's a transition which occurs here, and the roles switch. So we need to find 3 intersections in this case. So let's find the x-coordinates of the 3 intersections. And we'll use calc intersect, which is an invaluable tool on your TI-84, which you really need to know how to use. And you make sure that you use the 2 curves you're interested in, give an initial guess, and the calculator will be able to find that for you. And then the next thing we'll do is we'll actually store the contents of the x register, which has the result of that calculation, the x coordinate of that intersection point, and we'll store it into a different register for convenience and reference later. So once we do that, we can go back and repeat the process and find the other intersection points. So for example, we would go back and repeat the calculation, calc intersect, and each time we would return to the home screen and store it into the appropriate register. So we can get those coordinates stored to the highest precision the TI is able to find, and we can store those later and refer to them easily without having to type out these coordinates. So here's our first region. And we know our scheme, we need to integrate from A to B and the top minus the bottom. So this is exactly what the integral looks like. And what's nice is by using variable and function registers, we can actually write this integral as simply as it appears. So here our area of this first region is about 1.6595. Now there's a second region we need to add on. So there's this integral here, where we've switched the role of y1 and y2. And one of the things we could do is use second answer to retrieve the previous calculation, and then we'll add on the integral in question here. So the sum appears to be about 3.47. And again, please notice the use of second answer, which allows you always, for a new calculation, to insert the value of the previous calculation in your new calculation. So this can spare you some grief. So here's our area. And we'll notice that there's another way to calculate the area. We don't necessarily have to break this into two integrals if we're willing to use the absolute value operator. And what the absolute value does is it guarantees non-negative heights. So y1 minus y2 or y2 minus y1, they only differ by a multiplicative constant of -1. They're opposite of each other. So you could integrate from A to C and use the absolute value bar, and that would guarantee that you've done the same calculation. So here we'll repeat the calculation using absolute values for one integral, and we see that we get essentially the same result. But please notice it does take a while to come up with this result. This has something to do with the pointy nature of the function near this argument. And we'll also notice that these two don't agree completely all the way out to their full expansion. So there is something going on with the integral approximation process that is creating different results for these two different methods. So here are some tips for the TI-84. Use calc-intersect to find coordinates of intersection points. Use function and variable registers to make integrations as convenient as possible. And use answer and second enter to facilitate your calculations. Let's repeat this calculation using desmos. Now with desmos, finding intersections is as easy as clicking on the intersections. The downside is you only get about 3 decimals, and maybe 4 if you zoom in, of precision, but that's okay. We're going to store those into registers just like we did for the TI-84. This is for convenience. And so now we can simply write out in a new cell the integral. It's as easy as this. We can just use our names for the functions f and g and a, b, and c for the endpoints, and we can find our area just as easily as writing out this cell. And we'll notice also we could use the absolute value trick to write it as one integral. And by the way, you can see that even here, whatever method desmos uses to approximate definite integrals, these two methods don't quite agree. You get down to the end of their decimal expansions and they're not quite the same. Here's a new example. And this is going to be a little more subtle than the last one. So we've got an ellipse and a graph of the arctan function shifted up by a half, and we'd like to find this region right here. We can find the area between these curves two ways. First, by integrating with respect to x, and then by integrating with respect to y. With respect to x, we'd be moving in this direction for our integration, and we can imagine what the Riemann sum would look like. That's going to help us organize our thoughts to write out the integral. Here's our top, and here's our bottom. And we'll notice that the bottom function makes a transition at this argument. So if we integrate with respect to x, we're going to need to break this up into two integrals. If we integrate with respect to y, we can sort of turn our head to imagine that the integration will take place in this direction. Here's how the Riemann sum would look, so that helps us organize our thoughts. Here is the top, and here's the bottom. And we will notice that when we integrate with respect to y, the top function makes a transition here. So we will need two integrals. The upshot is that integrating either with respect to x or y is going to require us to break this into two integrals. So there's no advantage to go one way or the other. So we'll go both and practice both ways. Now we'll click on these intersections. We'll find the x and y coordinates, and since we're going to integrate with respect to both variables, we'll store all of these into registers a, b, p, and q. In passing, we should notice that we could use a calculator or other software to obtain higher precision if desired. So here, for example, we've asked Wolfram to find the intersection of these two curves. It gives us decimal expansions very far out. You could even find many more digits beyond what's practically useful. But the point here is that you could take these results and enter them here into Desmos if you wanted to create more precision for your intersection points if you wanted to do that. We won't though. So let's go back to our picture here. We could add labels. This would be a nice touch so that in the graph we can see what's going on. So inside of Desmos cells, you can actually just plot these points and put in the labels corresponding to the register names. Now, we have to do some algebra. To integrate with respect to x, we need to solve for y as a function of x. So we're going to take both of these, and in the top case, we'll solve for y, and we'll notice at this point, we need to take the square root. There are two roots, there's plus or minus. So we'll define the positive root to be given by this expression here, and the graph of this function is the top half of the ellipse. And then we will define another function, f sub n, the negative root, and this graph here constitutes the bottom of our ellipse. And of course, y equals arctan x plus 1/2 is already solved for y in terms of x, so we'll let g of x simply be our function arctan x plus 1/2. So here are the graphs of our three functions that we need to navigate this problem, and we'll go back into Desmos and we'll just double check. When we enter these formulas, we see that we get indeed the graphs we expected. So now we're ready to integrate. First, we'll find this little capped region off to the left. So the top is fp and the bottom is fn, and our integral then, we would go from -3 to a, and we'll integrate fp minus fn, and we get very close to 0.2. Now, we should point out there's some symmetry here with the ellipse. So we could actually simply integrate to find the top area and double it. And indeed, if you execute that integral in a Desmos cell, you will see that you get exactly the same quantity. So if you wanted to simplify your expression, you could do so. So that's that smidgen of the region. Now we need this area. Here's our top, and here's our bottom. And we go from A to P. So this is our integral, and we can write it in a new cell, and that will be this area on the right-hand side. Now, of course, we can just create a cell with both of these expressions added together, and that gives us our area. Our area is apparently just a smidgen above 7. And by the way, we've got some squares here we could just count off, and we can see that by building these rectangles, that sort of rectangular region has area 7, so it looks like we're in the right ballpark here. All right. Now we're going to integrate with respect to y. So in that case, we need to solve for x as a function of y. We're going to repeat this whole exercise, but this time we're going to solve for x in terms of y. Very similar sort of result. We have the possibility of two different roots when we take the square root. So we'll define new functions here, functions of y. Notice I'm using capital letters here. Desmos is going to recognize the difference between capital and lowercase. And I'm also creating functions of y. Now here we're going to invert. We'll take the tangent of both sides, and we get this expression for a new function, capital G of y equals tan of y minus 1/2. And so that should be this graph here. Now, to make sense of this all, you really should sort of turn your head a little bit and see that we're solving for x as a function of y, and these are all graphs of functions in that context. We can enter these formulas into Desmos, and Desmos handles functions of y quite reasonably, and we can check that we get everything. Notice we get some bonus graph here because, why do we see this? We didn't see this before. We see this because the arctangent function and the tangent function aren't truly inverse to each other, and this bonus graph we're seeing is a consequence of that fact. But it doesn't actually affect our calculations. We're just seeing more than we expected. Let's find the region of this top cap. Now this is our integration direction, and there's our top function, and there's our bottom function. And so here's our integral. We're going to integrate from q, being the smallest value of our integration variable y, to 2, the largest value of our integration variable y, and we get a little over 1. And as previously with the cap on the left side, there's some symmetry here. We could simply calculate this region on the right and double it, and you can see that you get the same quantity. Now we need to add on this region, the area of this region. So here's our top function, and here's our bottom function as functions of y. Integrating in this direction, so our integration should go from b to q. And here is the area of the missing region. Now we're going to add these together, and we get about 7 and some spare change, and that is exactly, in fact, what we got using the other method, although, once again, It's interesting to point out that these decimal expansions don't quite agree beyond about 6 or 7 places. And that just has to do with approximations. Our precision wasn't all that great with our numbers. We stopped after 3 decimals. There are many reasons this could happen, but this is in fact the same result, just not the precisions don't match.